Yeah, no, sorry. I made it yesterday, but then I forgot to change the page. Good. Okay, so assignment 6.1 was basically applying Dijkstra's theory. So the book has a slightly different approach. So the Dijkstra works far better. So just use Dijkstra's. So in this case, if we look at the model, if we look in here on the top right, we see the model. Well, we basically have 7 nodes. So we have the origin, 5 intermediate nodes, and the destination. So that means we have a total of 7. So basically means we need 7 equality constraints for this model. There's no capacity limits on the links, so we don't need any. So we don't need anything like that. So we have actually 5 equality constraints, and we have, let's say, a 1 with a 7 equality, but one has a plus 1, one has a minus 1, and 5 have a 0 flow. Well, there's 12 links, so that means there's 12 variables, so each link has its own variable. It's either used or it's not used. And if we then look here at the original table, then if we've had A and C, then actually the next nearest one is B, which is a distance of 50 from A. So if we go A to C, then the next one is B. After we've connected B, then B, if you look here, then B will connect to C, D, and E. Well, C was already connected, so we can ignore that. It will always be longer than the connection we've already found. And D and E are 55 and 40, so D and E are now added, with in this case 105. D was also added before because D was also connected to A. But that's actually a shorter path, and E is now a new connection of 100, so that's 50 plus 50. If we then look at the path, and then if we finish it, basically we get this table, and what we then have to do is we have to start at the end. T, the node previous to that was D, so T, D, D, B, B, A, A, O. So TDBBAO is actually the reverse route, so then the middle route is OABDT, and that's a distance of 165. Yeah, so you have to be careful. Of course, normally you don't do this by hand, but you program an algorithm to do it for you, but it's always good to know what your algorithm is doing. So, so the same thing, but now with a minimum spanning tree. So if we have O, A, and B solved, then we can basically, the next options are C, D, and E, and then C from B. So if you look, so A, B, A and B already solved, so we can ignore those. So the next options are C, D, and C and D. Well, C is 50 or 20, and D is 70. So C with 20 is actually the shortest one, so that's actually the next node we'll connect. And that will open up the connection to E. Another connection to E, which is then actually longer than the connection we already had. So after that, we'll actually go to E. So if we then if we finish the table, we basically get this, and we get that the total span will end up being 180. So that's basically all of these added up. So it's simple enough. So the minimum spanning tree from an algorithm point of view is a fairly easy one. So it's also fairly easy to program. And again, the spanning tree comes back when we look at the network simplex method, because it's the format we need to basically create the cycles there. So 6.2, what we're actually doing is we have a flow algorithm, and we're using that. So it's not really shortest path algorithm. But we simply have a flow of 1, and we're pushing that through the network with a minimum cost. So we have a minimum cost flow with 1. Well, if we look from node 25 to 28, it's 1450. So you see the route here. 4 is not part of that route, so that was the proper answer. If you go the other way around, because we have one-way links, you actually see that from 28 to 25 is actually longer, because we have a one-way route. So we actually have a different route. We have one-way links, so we actually have a different route from 28 to 25 than from 25 to 28. So if you then, so this is one of the things I did. If you want to get an alternate route, then well, there are a couple of ways of doing that. But the way I used, in this case, because I really want a route which has as little to do with the other route as possible. What we do is basically we take the first route, we penalize all the parts of the first route. We can't just block them because then actually we'll probably end up with no route because there's links it will have to use, but it will push it away from using them. So in this case, we use a distance penalty factor of 2. So basically, we multiply everything on that route with a factor of 2. So then the distance, of course, for that route will double. Now we can re-optimize it. Now we get a new number. And in that case, if we then restore the real distances, we see actually that about 600 length of the original route is still used, even though the penalty, but 1450 is actually different. So 2050 minus 600. So 600 is over the same route, and the 1450 actually takes a different route. So this way we can get a real alternate route which has as little to do as possible with the original one. It's like if you have with Google, if you use Google Maps to plan your route, you don't want it to tell you to, well, if you want to go home, it probably has the fastest route, and then it will show you an alternate, but what you don't want to hear is that you go on one block and then drive back, because that doesn't make any sense. You really want a route which is significantly different and avoids all the roads in the original route. So this is a way of doing that. Assignment 6.3. So we basically have this model here. We're going to use that for an augmented path algorithm. Basically, we have 10 links plus an inflow and an outflow. So for the LP, you can do what you want. You can, but in this case, I think it's well, especially for like a maximum flow, it's better just to add 2 variables, one for the inflow and maybe even one for the outflow. So the outflow you can also leave open. So make sure you constrain from this node actually a larger equal to 0 constraint. But if you just put an inflow and outflow, it's also easier just to read the result. So we have 12 variables. Yeah, so we have the 10 links, inflow and outflow, so that's 12 variables. We have 7 nodes. In this case, also we have capacity limits on the links, so that's those are also 10 extra constraints. But we can also model these as upper bounds. So we can also put them into the upper bounds, and that's last week I showed you the upper bound technique, so it makes it solving in some cases slightly more handy. So if you look at node 3, then in node 3 we have x1, 3 coming in, and then we have 3, 4, 3, 5, and 3, 6 coming out. So it's 3, 5 in, 3, 4, 3, 4, 3, 5, and 3, 6 coming out with a plus, and of course it has to be equal to 0. It's an intermediate node, so the net flow has to be 0. If we look at adding the path, then 1, 2, 5, 7 is actually the first path we'll add, and then we'll see it has a capacity of 6, 4, and 4. Well, 4 is the minimum number, so in this case, 4 is the flow, and that means that the link from 1 to 2 actually still has 2 flow remaining, which we can maybe then use for another. Of course, in this case, there's no other route using this, so in this case, it will remain unused. Well, then we can add path 1, 3, 6, 7, which has a minimum of which has a capacity of 3, so 4, 3, 9. So 3 is the maximum over this path, so this one still has 1 remaining. This one still has 6 remaining. We could have also taken 1, 3, 4, 6, 7. That's why it asks for the shortest one, so this one is slightly longer, but it also has a maximum capacity of 3. But we'll take the shorter one first, and of course, after we've actually removed this, then there's only 1 remaining here, so then this the 1, 3, 4, 6, 7 path will only have a remaining capacity of 1. Because there's only 1 more capacity remaining than 3. And then finally we add 1, 4, 6, 7, so 1, 4, and 6, 7. Well, the capacity here is only 1, and then we get to a total of 9. So the maximum flow in this case is 9. Well, if you use this table, so if we take the first instance, so what is it? 1, 2, 5, 7. So we start with 1, 2, 5, 1, 2, 5, 7. So that basically we get a path here. So 1, 2, 5, 7. And then when you cross it, you basically move that to the other direction. So here we have a flow of, let's see, 4, 4, and 4. And then here we add it up. Here on the last table here, it actually means something because this is then your total flow. keep track of. Intermediate, especially with backflows, the numbers here don't necessarily mean something, but I just like to put it there, and then because again, if you return a flow, then actually you should retract it, so it doesn't quite work. So the numbers here don't really mean anything except that you have done some flow through it. So, but here the last one, it does actually say something. So this way, it's nicer to keep track of, and it's nicer to copy paste. Any questions about this? Okay, 6.4. Well, here we again use the IOR tutorial. I did it actually without. So we have 6 nodes plus 9 links, so we have to have 15 constraints in total if we want to create an LP problem like this. AF is actually, even if you do put it in, so that's a bypass flow, it has no capacity limit, so we will not add a constraint. Yeah, but it will of course add a variable. So that's why I didn't ask you the number of variables. So if you want to maximize the network flow, maximize network flow, then actually what we have to, or the maximize, we want to minimize the bypass flow. The bypass flow basically has a cost, and we want to minimize that cost. So we put a flow of 20 on it, which is certainly more than we think the network will handle. But we'll start with 2 flows, A, B, D, and F. So this one, and A, C, E, and F. And in this case, if we look at this flow, we have a capacity of 9, 7, and 6. So the capacity limited to 6. So this one is limited, so we have a flow of 6 over this one. Also, we have a flow over this one, because in this case, CE is limiting. Well, if we add these, and also then add A to the bypass flow, then we have a closed loop. So we need to create a spanning tree. So we need to break the loop, and the places to do that is places which are at maximum flow. So D and F, we can reverse C and E. So there, basically, we replace a basic variable by a non-basic variable by reversing it. So then we take the full flow in this case, and now we have full flow here and 0 flow there. So the full flow is a constant, and then the 0 flow is a non-basic variable. So now we have indeed a spanning tree here where there's no closed cycles. So if we now look at BE, shown here, if we add BE, then we're actually creating a cycle like this. So if we add something to BE, we'll have to add to AB and to EF, and we'll remove it from AF, and of course that is a positive from a cost point of view, right? Because it reduces our cost, because we're trying to reduce this flow. So here we'll add, here we'll add, here we'll add, and here we'll remove. Then if we look actually what is maximum capacity, well, we can add 3 here, 2 here, and 3 here. So actually BE is actually the most limiting in capacity here, so we can't add more than 2 flow there. So what you'll see happening there is that BE actually goes to basic and immediately gets reversed to stop it from becoming a full cycle. So it will actually be reversed and it will be replaced by a non-basic reverse flow. So in this case, actually the entering and leaving basic variable is the same, which can happen with the network simplex method. So and then if we add ABDF, ABDEF, so if we have this flow remaining, we can add 1 flow over here. In this case, BD, well, we already added 2 here, so there's only 1 here, and there's only 1 flow remaining here. So we basically now have a flow going here. It has a maximum capacity of 1. And now we can either reverse this one, or this one. So in this case, we're actually free to choose it, and it doesn't really matter which one we actually reverse. Each one we reverse will actually get we'll keep a spanning tree. So we have to take care of that. We keep a spanning tree, you don't have any short circuits. And then actually there's no capacity over this line anymore. So you see actually over this line, there's no capacity, so we can't add any more flow to it. Yeah? So then we know we have our optimum, and then, well, the remaining over AF is 5, so we actually have 15 flow going through our network, which of course is 6 plus 9. Yep. Good. That's it. I'll post these on Brightspace. If you have any questions, let me know. Also, I hope you've all signed for groups. I think it's probably closed now, but if you haven't signed yet, please come to me and then we'll have a look, and I can see maybe if I can add you to another group. And if you have other questions, I'll be ready. Good luck.